Picture this. An invisible web of power stretches across the cosmos, twisting star systems into shape, guiding the birth of galaxies, and even bending the fabric of space itself. This isn't science fiction, it's the hidden force of cosmic magnetism, and its secrets are some of the most tantalizing puzzles in the universe. Think about the last time you held a magnet, feeling that faint pull between your fingers. Now, imagine that same force, but scaled up to the size of a black hole, with enough power to rip atoms apart or warp the paths of entire stars. That's the scale of the mysteries we're about to explore. For centuries, humans have looked up at the night sky and wondered what shapes the heavens. We've mapped planets, traced the orbits of comets, and even glimpsed the edges of black holes. But there's an invisible hand at work behind it all, a force so pervasive that without it, the universe as we know it wouldn't exist. Magnetism doesn't just hold your fridge notes in place. It's the silent architect of cosmic storms, the hidden trigger behind solar flares, and the mysterious glue that holds star clusters together. And yet, despite its overwhelming influence, we've only begun to scratch the surface of how it truly works. That's where our journey begins. Over the course of this exploration, we'll unravel 30 of the most compelling magnetic puzzles scattered across the cosmos. Why does the Sun's magnetic field suddenly flip every 11 years, like a cosmic switch? How can a magnetar, a city-sized remnant of a dead star, generate a magnetic field so strong it could erase your credit card from halfway across the galaxy? And what role does magnetism play in the birth of new stars or the violent deaths of old ones? These aren't just abstract questions, they're the keys to understanding the very forces that shape existence. So get ready to dive deep into a world where the rules of physics twist into strange new shapes, where invisible fields hold unimaginable power, and where every answer leads to even more thrilling questions. The cosmos is calling. Let's uncover its magnetic secrets together. Our first cosmic magnetic riddle takes us straight to the heart of our solar system, the Sun. Every 11 years, like clockwork, something extraordinary happens. The Sun's entire magnetic field flips. North becomes south, south becomes north, as if someone flipped a giant cosmic switch. But here's the twist, we still don't fully understand why. Think of the Sun as a seething cauldron of superheated plasma, where charged particles swirl in massive currents. Deep beneath its fiery surface, these flows act like a colossal engine, generating magnetic fields through what scientists call the solar dynamo. Over time, these magnetic fields grow tangled, like a ball of yarn twisted too tightly, until they snap and reverse polarity. It's as if the Sun hits a reset button, untangling its magnetic knots and starting the cycle all over again. But the real mystery isn't just the flip itself, it's the precision of that 11-year rhythm. What keeps this cosmic metronome ticking so reliably? Recent missions like NASA's Parker Solar Probe have ventured closer to the Sun than ever before, diving through its scorching atmosphere to study these magnetic dances up close. What they've found is a turbulent world of plasma rivers and magnetic whirlpools, with energy churning in ways we never expected. Some researchers believe these hidden flows act like a conveyor belt, dragging magnetic fields along until they're stretched, twisted, and finally flipped. And here's where things get even more intriguing. This magnetic reversal isn't just a curiosity. It's directly tied to solar storms, those violent eruptions that can knock out satellites, disrupt power grids, and even pose risks to astronauts. If we could crack the code of the Sun's magnetic flip, we might finally predict these space weather events before they strike. Imagine a future where we get advanced warning before a solar storm fries our electronics, all because we unraveled the sun's magnetic secrets. So while the 11-year cycle might seem like a simple back and forth, it's really a cosmic balancing act, a delicate interplay of forces we're only beginning to grasp. And with every new discovery, we're peeling back another layer of the sun's magnetic mystery, one flip at a time. If the sun's magnetic flip is a cosmic metronome, then magnetars are the universe's wrecking balls, neutron stars so magnetically charged they defy everything we know about physics. Picture a star so dense, a teaspoon of its material would weigh 1 billion tons, spinning faster than a blender blade, wrapped in a magnetic field so strong it could tear the electrons right off your atoms from thousands of light years away. These aren't just magnets, they're monsters. How does something so ferocious come to exist? When a massive star dies in a supernova, its core doesn't just fade quietly, it collapses into a neutron star, a city-sized cinder spinning at dizzying speeds. But sometimes, under conditions we're still piecing together, that collapse goes haywire. The star's original magnetic field, already intense, gets amplified beyond comprehension as the star's core twists and churns like a dynamo gone rogue. Think of it like wringing out a wet towel, except instead of water, you're squeezing spacetime itself, twisting magnetic field lines until they're tighter than a coiled spring. The result, a magnetar with a magnetic field 1,000,000,000 times stronger than Earth's, humming with enough energy to crack the star's crust in violent starquakes. And when those quakes happen, the universe feels it. Magnetars don't just sit quietly, they scream. In 2004, a magnetar 50,000 light-years away let out a gamma ray burst so powerful it briefly ionized Earth's upper atmosphere despite being halfway across the galaxy. If one erupted within just 10 light-years of us, the blast would strip away our ozone layer, triggering mass extinctions and frying every unshielded electronic device on the planet. Satellites would blink out, power grids would surge and melt, and the auroras would be visible at the equator. Yet for all their destructive potential, magnetars might also be cosmic lighthouses, helping us map the universe. Their pulses of X-rays and radio waves are so precise, scientists use them to test Einstein's theory of relativity in extreme gravity. Some researchers even suspect these magnetic beasts could be the source of mysterious deep space signals like fast radio bursts, flashes of energy so intense they outshine entire galaxies for milliseconds. So while we might never see a magnetar up close, their fingerprints are everywhere. They remind us that the universe isn't just vast, it's volatile, unpredictable, and brimming with forces we're only beginning to measure. And somewhere out there, right now, one of these magnetic titans is winding up for its next cataclysmic roar. Hidden beneath the Milky Way's glittering spiral arms lies an architecture far stranger than anything we can see, a vast, invisible lattice of magnetic fields stretching tens of thousands of light-years across our galaxy. If you could glimpse this cosmic web, it would look like threads of force woven through space, bending the paths of cosmic rays, cradling newborn stars, and even guiding entire clouds of gas into the shapes we recognize as constellations. But here's the catch: we've only just begun to map this ghostly framework, and its origins remain one of the most hotly debated mysteries in astrophysics. Picture the Milky Way not just as a collection of stars, but as a colossal magnetic tapestry. Some of these fields are faint, barely stronger than Earth's, while others crackle with enough energy to accelerate particles to nearly the speed of light. Astronomers detect them indirectly, like tracking invisible ink under ultraviolet light. When starlight passes through these fields, it becomes polarized, vibrating in a distinct direction that betrays the magnetic web's presence. The patterns they've uncovered are astonishing. Some regions look like tangled yarn, others form sweeping arcs, and near the galactic center, they twist into chaotic knots as if space itself is tied in magnetic shoelaces. But where does this web come from? One theory suggests these fields are primordial, imprinted on the universe in its earliest moments, when the cosmos was a seething plasma soup. As galaxies formed, they may have dragged these ancient magnetic threads along like cosmic lint, preserving relics from the dawn of time. Others argue supernovae are the real architects. When massive stars explode, they blast out shock waves that stretch and amplify magnetic fields, weaving them into the galaxy's fabric like a blacksmith hammering molten metal. There's even a wild card: supermassive black holes. The one at our galaxy's heart, Sagittarius A star, could be acting like a loom, spinning jets of charged particles that embroider magnetic patterns far into the void. What's at stake isn't just academic. This invisible web shapes how stars are born. Giant molecular clouds, the nurseries where stars ignite, can't collapse into new suns without magnetic fields gently nudging them into place. Without this hidden scaffolding, our galaxy might look utterly different. Fewer stars, fewer planets, perhaps even no Earth. And for future space travelers, these fields are both shield and threat. They deflect deadly cosmic rays, but also funnel them into hypercharged corridors that could fry unprotected electronics. The deeper we look, the more questions arise. Why do some galaxies have stronger magnetic fields than others? How do these fields survive collisions when galaxies merge? Each answer pulls us closer to understanding not just our own Milky Way, but the magnetic heartbeat of the universe itself. And with new telescopes like the Square Kilometre Array coming online, capable of mapping these fields in unprecedented detail, we're on the verge of decoding a galactic language written in lines of force, one invisible thread at a time. Imagine standing on the surface of Mars, staring up at a sky that once held oceans and a thick atmosphere, now stripped away by the relentless solar wind. The difference between our blue planet and that barren red desert, a magnetic field. Earth's invisible shield deflects deadly radiation, preserving our atmosphere and making life possible. But Mars, once so similar to us, lost its protective cloak billions of years ago. So why do some planets hold onto their magnetic fields while others let them fade? The answer lies deep beneath their surfaces, in the hidden churn of molten metal and the slow death of planetary cores. Let's start with Earth, our magnetic fortress. Our planet's field isn't generated by some solid bar of iron at the center. It's alive, a swirling ocean of liquid iron and nickel in the outer core, superheated to nearly 5,000 degrees Celsius. As the planet rotates, this molten metal twists and folds like boiling water in a pot, creating electric currents that birth our magnetic field. It's called the dynamo effect, and it's the same principle that powers a bicycle light movement generating electricity, just on a planetary scale. Without this churning core, Earth's atmosphere would have been torn away by solar winds long ago, leaving us as lifeless as Mars. Now, look at Mars. Billions of years back, it likely had a magnetic field just as strong as ours, protecting rivers and maybe even microbial life. But Mars is smaller, about half Earth size, and that made all the difference. Smaller planets lose heat faster, and as Mars' core cooled, its molten iron solidified, shutting off the dynamo like a stalled engine. Once the field vanished, solar winds had free rein, blasting away the atmosphere molecule by molecule until the planet became the frozen desert we see today. But then there's Jupiter, the solar system's magnetic heavyweight. Its field isn't just stronger than Earth's, it's 20,000 times stronger. A monster so vast it stretches millions of miles into space, deflecting radiation that would fry entire moons. The secret: Jupiter doesn't even have a traditional iron core. Instead, its magnetic might comes from a bizarre form of matter-metallic hydrogen. Under the crushing pressure of Jupiter's interior, hydrogen gas transforms into a liquid metal, flowing with electric currents that generate a magnetic behemoth. This cosmic lottery of magnetic fields raises a tantalizing question. Could we one day jump-start Mars' dynamo, giving it a magnetic shield again? Some scientists think so. Ideas range from orbiting superconducting rings that create an artificial magnetosphere to drilling deep into Mars' core to re-liquefy its iron with nuclear reactors. It sounds like science fiction, but if we crack the code, we might not just protect future Martian colonies. We could even rebuild its atmosphere, turning the red planet green. The lesson here is simple. Magnetic fields aren't just cosmic quirks. They're the guardians of worlds, the difference between a living planet and a dead one. And as we search for life beyond our solar system, spotting magnetic fields around distant exoplanets might be our best clue to finding the next Earth or avoiding the next Mars. One of the most baffling signals from the cosmos arrives in bursts shorter than a blink-fast radio bursts, or FRB. These incredibly powerful flashes of radio waves last just milliseconds, but in that fraction of a second, they release as much energy as the Sun does in 3 days. Some of them even repeat, firing off like a cosmic Morse code with patterns we can't yet decipher. But here's where magnetism enters the puzzle. Many of these bursts arrive twisted, their waves polarized in ways that suggest they've traveled through some of the most extreme magnetic fields in the universe. Take the case of FRB 200428, detected in 2020. When astronomers analyzed its signal, they found its waves were so tightly wound, it was as if the burst had spiraled through a magnetic whirlpool. The only known objects capable of warping light like that, magnetars, these ultramagnetic neutron stars with fields a quadrillion times stronger than Earth's, could be the cosmic culprits behind at least some of these bursts. Picture a magnetar's crust cracking under magnetic strain, a starquake so violent, it sends shock waves rippling through the surrounding magnetic field. Those shocks could accelerate particles to near light speeds, generating the intense radio flashes we detect as FRBs. But not all FRBs fit this mold. Some repeat at intervals that don't match any known magnetar behavior, while others seem to come from regions of space with no obvious stellar remnants. This has led to wilder theories. Could some FRBs be produced when black holes and neutron stars collide, their merging magnetic fields snapping like rubber bands? Or perhaps they're the result of cosmic strings, hypothetical defects in spacetime itself, vibrating like plucked guitar strings under magnetic tension. The most tantalizing possibility, FRBs might be our first glimpse of quantum gravity effects, where the fabric of spacetime warps so severely under magnetic pressure that it reveals laws of physics beyond Einstein's theories. What makes these bursts so revolutionary isn't just their mystery, it's what they're teaching us about magnetism's role in shaping the universe. Every polarized FRB is like a fingerprint, carrying traces of the magnetic environments it's traveled through. By decoding these signals, we're essentially mapping the universe's hidden magnetic highways, from the turbulent outskirts of galaxies to the voids between them. And with new telescopes like the CHIME array detecting dozens of FRBs every month, we're closer than ever to solving one of astronomy's greatest riddles. Are these bursts the screams of dying magnetars, the birth cries of new physics, or something even stranger? One thing's certain: wherever magnetism stretches to its limits, the universe finds a way to surprise us. Cosmic jets are the universe's particle accelerators, firing beams of supercharged plasma across thousands of light-years with pinpoint precision. These dazzling streaks, whether erupting from newborn stars or the maws of supermassive black holes, defy intuition. How can a chaotic, swirling vortex of gas and dust produce a laser-straight jet, as if some invisible hand is guiding it? The answer lies in magnetism's invisible scaffolding, shaping chaos into order with forces we're only beginning to measure. Take Herbig-Haro objects, for example, the birth cries of young stars. As a protostar gathers mass, it doesn't just pull material inward. Some of it gets hurled back out in opposing jets, moving at 500,000 miles per hour. But without magnetic fields, these jets would spray outward in all directions like a garden hose with no nozzle. Instead, they stay tightly focused, piercing through interstellar clouds like celestial spears. The secret spiral magnetic field lines wrapped around the star's poles, acting like a cosmic particle collimator. As ionized gas spirals along these fields, it gets funneled into narrow beams, accelerated to velocities that would make a bullet look slow. Then there's the other extreme, jets from supermassive black holes like the one in Galaxy M87, which stretches 5,000 light-years into space. Here, magnetic fields don't just guide the jets, they're the engine. Near the black hole's event horizon, plasma gets trapped in magnetic loops that stretch, snap, and reconnect in violent explosions called magnetic reconnection. It's like cracking a cosmic whip. The sudden release of energy flings particles outward at nearly light speed, while the black hole's rotation twists the magnetic field into a helix, keeping the jet razor straight across unimaginable distances. But the real mystery isn't just how these jets form, it's how they shine. Particles in the jets should lose energy over time, yet we detect them blazing brightly millions of light-years away. The likely culprit, turbulent magnetic fields within the jets themselves. As particles spiral around these fields, they emit synchrotron radiation light produced by charged particles dancing to magnetism's tune. This same process might explain why some jets flicker unpredictably, as internal magnetic storms boost their brightness in sudden flares. What's astonishing is how universal this mechanism seems. From tiny protostars to galaxies with black holes billions of times the sun's mass, magnetism sculpts these jets with eerie consistency. Some researchers even suspect cosmic jets seeded the early universe with heavy elements, spraying enriched material across space like cosmic fire hoses. Others theorize they regulate galaxy growth without these magnetic exhaust pipes. Black holes might overheat, choking on their own infalling gas. The more we study these jets, the clearer it becomes. Magnetism isn't just a side character in the cosmos. It's the director, choreographing some of the most violent and beautiful phenomena in existence. And with next-generation telescopes like the Event Horizon Telescope refining their focus, we're closer than ever to catching this magnetic maestro in the act. Deep beneath our feet, Earth's magnetic north isn't where it used to be. In fact, it's racing across the Arctic at breakneck speed, up to 34 miles per year, forcing scientists to update the world magnetic model ahead of schedule just to keep GPS systems accurate. This isn't some gradual drift, it's a full-blown magnetic sprint, and it's exposing cracks in our understanding of the planet's hidden engine. What's driving this erratic motion? The answer lies 1,500 miles below the surface, in the churning ocean of molten iron that makes up Earth's outer core. Here, rivers of liquid metal swirl like boiling water in a pot, generating electric currents that power our magnetic field. But lately, something's stirring the pot more violently. Satellite data reveals turbulent flows beneath Canada and Siberia, where molten iron is sloshing in ways models didn't predict. Some researchers suspect these disruptions are caused by a high-speed jet of liquid iron, a subterranean current racing westward under Alaska like a hidden conveyor belt, dragging the magnetic pole along with it. The real question isn't just why the pole is moving, it's where this could lead. Earth's magnetic field has flipped hundreds of times in its history, with north and south swapping places. These reversals aren't tidy, they take centuries, during which our protective shield weakens, sometimes to as little as 10% of its normal strength. The last full reversal, 780,000 years ago, coincided with a surge in cosmic rays hitting the planet, leaving traces in ancient rocks. If that happened today, the consequences would be stark. Satellites bombarded by solar radiation could fail en masse, power grids might overload during solar storms, and migratory animals from whales to birds could lose their natural compasses. Yet here's the twist: we're overdue for a flip by geologic standards, but the current wonder doesn't necessarily signal an imminent reversal. The field's strength has dropped about 10% over the past century and a half, but it's still stronger than it was during many stable periods in Earth's past. Some scientists argue the pole's movement could just be part of a normal oscillation, like a wobbling top that eventually steadies itself. Others point to strange anomalies like the South Atlantic anomaly, a growing weak spot where satellites already suffer higher radiation exposure, as potential early warning signs. One thing's certain: the more we learn, the stranger the picture becomes. Ancient clay tablets from Mesopotamia reveal that 3,000 years ago, Earth's magnetic field was nearly 30% stronger than today. Ice cores from Antarctica show spikes in radioactive isotopes during past weak periods, proof of heightened cosmic bombardment. Even more intriguing are hints that reversals might cluster in time, suggesting some larger cycle we haven't deciphered yet. As tech-dependent as our species has become, understanding this magnetic dance isn't just academic, it's survival. From recalibrating airport runways to shielding astronauts from solar flares, every tweak in the poles ripples through modern life. And while we can't stop the core's restless churn, unraveling its patterns might one day let us predict its next move before our compasses spin wildly and the auroras blaze in places they've never been seen before. Inside the dark, swirling clouds where stars are born, there's an invisible tug of war raging between two cosmic forces: gravity pulling material inward and magnetism pushing back like an unseen hand. These stellar nurseries, vast, cold regions of gas and dust, should collapse quickly under their own weight, forming stars in a cosmic blink. Yet something slows the process down, stretching what should take thousands of years into millions. That cosmic break: magnetic fields threading through the chaos like invisible wires holding back the storm. Take the Taurus molecular cloud, one of the closest star-forming regions to Earth. When astronomers mapped its magnetic fields using instruments like the ULMA telescope, they didn't find random tangles. They discovered vast, organized lines of force, like the pattern of iron filings around a bar magnet. These fields act like scaffolding, propping up the cloud against gravity's relentless pull. Charged particles, unable to cross the field lines, get trapped, slowing the collapse. It's as if the universe itself is pacing the birth of stars, ensuring they don't form too fast or too chaotically. But here's where it gets even more fascinating. Sometimes these magnetic fields don't just resist collapse, they guide it. In the Orion Nebula, ULMA spotted something extraordinary: magnetic fields channeling gas into dense filaments, like rivers funneling into a canyon. Where these streams converge, gravity finally wins and baby stars ignite. And when the fields weaken or twist into knots, something remarkable happens: the gas fragments, not into one star, but into pairs or even clusters. This might explain why so many stars have siblings. magnetism doesn't just slow star birth, it shapes stellar families. The most stunning evidence comes from protostellar disks, the swirling platters of gas where planets form. These disks shouldn't spin smoothly for long. Friction should make them spiral inward in a cosmic drain. Yet they persist, and magnetism is the likely culprit. Fields act like cosmic shock absorbers, transferring energy from the inner disk to the outer edges, stabilizing the system. Without this balancing act, planets might never have the time or material to form. What's emerging is a picture of magnetism as the universe's great architect. It doesn't just oppose gravity, it collaborates with it, ensuring stars are born not in chaos, but with a strange, beautiful order. And as telescopes peer deeper into these stellar nurseries, we're learning that the same forces shaping stars might also shape their planets, their moons, and perhaps even the conditions for life itself. Cosmos doesn't just build stars, it crafts them, with magnetism holding the chisel. The moon today is a silent, barren world, lacking the protective magnetic embrace that Earth enjoys, but it wasn't always this way. Apollo astronauts brought back rock samples in the late 1960s and early 70s, and when scientists examined them, they found something astonishing: tiny grains of magnetized minerals, frozen in time like cosmic compass needles pointing to a lost era. These rocks tell us that billions of years ago, the moon's magnetic field wasn't just present, it was as strong as Earth's is today. So what happened to it? And how could a world just 1% of Earth's mass once generate such a powerful shield? One leading theory points to the moon's molten core. Early in its history, the moon's interior was hot enough to keep iron flowing in a liquid state, churning like Earth's outer core and potentially fueling a dynamo effect. But being so much smaller, the moon cooled rapidly. Without the heat to sustain convection, the dynamo sputtered out, and the magnetic field faded into silence. Yet there's a problem with this neat explanation. Some lunar rocks suggest the field persisted for far longer than simple cooling should allow, lingering for over 1 billion years. That's like a campfire staying hot long after the last log burned to ash. This inconsistency has led to wilder ideas. Maybe the moon's dynamo wasn't driven by heat alone. Some scientists propose that giant asteroid impacts, which were frequent in the early solar system, could have violently stirred the lunar core, jump-starting its magnetism like a cosmic defibrillator. Others speculate that the moon's orbit played a role. Its gravitational dance with Earth might have stretched and squeezed its interior, creating friction that kept the core churning. There's even a fringe theory that the moon's crust itself acted as a temporary magnetic battery, charged by the solar wind and discharging over eons. The stakes here go far beyond lunar geology. If we can crack the mystery of the moon's lost field, we might unlock secrets about other small rocky worlds like Mercury, which somehow maintains a weak magnetic field despite its tiny size, or Mars, whose dead dynamo doomed its atmosphere. Future missions like NASA's planned lunar rover Viper could hunt for more magnetic clues in the moon's ancient rocks. And if we find evidence that impacts or orbital forces powered its dynamo, it could rewrite the rules for how we search for habitable exoplanets. After all, a magnetic shield isn't just a cosmic accessory, it's often the difference between a living world and a lifeless one. So while the moon's magnetic whisper has faded to silence, its story is far from over. Every magnetized rock is a time capsule, holding clues to a time when our closest neighbor was a far more dynamic world, one that might yet teach us how magnetism shapes the destiny of planets. Galaxies aren't just islands of stars, they're colossal electromagnets, wrapped in invisible fields that stretch hundreds of thousands of light years. But here's the puzzle: how does something as vast as a galaxy become magnetized in the first place? Unlike a simple bar magnet, galaxies don't have an obvious on switch. Their magnetic fields are woven into their very fabric, threading through spiral arms and swirling around supermassive black holes. And the more we study them, the stranger the story gets. One clue comes from the early universe, a time when space was a seething plasma soup. Even in that chaos, tiny magnetic fields might have flickered into existence, random fluctuations in the primordial particle sea. These weak seed fields could have been stretched and amplified over billions of years as galaxies formed, like blowing up a microscopic doodle into a cosmic mural. How turbulence is the key. As gas clouds collapsed to form galaxies, their chaotic motions acted like a natural dynamo, twisting and folding these fledgling fields until they grew strong enough to shape entire galactic structures. But there's a rival theory that's even more dramatic. At the heart of every galaxy like ours sits a supermassive black hole, and these monsters might be cosmic electromagnets in disguise. When black holes feed, they don't just swallow matter, they spew out jets of plasma at near light speed, laced with magnetic energy. Some researchers argue these jets could be injecting fresh magnetic fields into their host galaxies, like a sculptor molding clay. The evidence: galaxies with active black holes often have stronger, more organized magnetic fields, as if the black hole's influence is still echoing through the cosmos. Then there's the wild card: cosmic collisions. When galaxies merge, their magnetic fields don't just cancel out, they tangle, reconnect, and sometimes emerge stronger than before. Observations of colliding galaxies show magnetic filaments stretching between them, like threads stitching two cosmic tapestries together. This suggests magnetism isn't just a passive feature of galaxies. It's a dynamic force that evolves with them, growing stronger through violence and chaos. What's at stake isn't just an academic debate. Galactic magnetic fields shape how stars form, how cosmic rays travel, and even how black holes grow. They might explain why some galaxies become star-forming powerhouses while others quiet down into retirement. And if we can crack the code of how these fields arise, we could unlock secrets about the universe's earliest moments, traces of magnetism that predate the first stars. New telescopes like the Square Kilometre Array are poised to revolutionize this search, mapping galactic magnetism in unprecedented detail. Already, they've spotted hints of magnetic fields in the voids between galaxies, faint whispers of a cosmic web far larger than we ever imagined. Every discovery pulls us closer to answering the ultimate question: is magnetism woven into the universe's blueprint, or is it forged in the fires of galactic evolution? One thing's certain: the answer lies somewhere in the invisible threads tying the cosmos together. Most planets in our solar system play by the rules. Their magnetic fields line up neatly with their rotation axes, like a spinning top perfectly balanced on its point. But Uranus and Neptune, they're cosmic rebels, flipping the script with magnetic fields that twist at bizarre angles, as if someone tilted the universe's compass. Uranus' field juts out at a staggering 59-degree angle, while Neptune's is not only off-center but lopsided, with one hemisphere's magnetism significantly stronger than the other. These aren't just quirks, they're windows into the strangest interiors in our solar system, where the usual rules of physics take a backseat to something far more exotic. So what's warping these magnetic fields so dramatically? For Uranus, the leading suspect is a cataclysmic past. Imagine a young Uranus spinning peacefully until a colossal impact, perhaps by an Earth-sized object, knocks it sideways, leaving the planet spinning on its side like a cosmic bowling pin. But here's the twist: an impact alone can't explain the magnetic oddities. Deep beneath its icy clouds, Uranus might harbor an ocean of supersonic water, a bizarre state of matter where water molecules break apart under extreme pressure, forming a crystalline lattice of oxygen ions with hydrogen nuclei flowing through it like a liquid metal. This electrified slush, churning in a tilted planet, could be generating a magnetic field that's as off-kilter as Uranus itself. Neptune's lopsided field is even more puzzling. Unlike Uranus, Neptune wasn't knocked sideways, it spins upright, yet its magnetic field is wildly asymmetric, clustered more toward one hemisphere, the culprit. Scientists suspect a hidden layer of ammonia-rich fluid deep inside the planet, behaving like a cosmic short-circuit. On Earth, ammonia is a simple cleaning agent. On Neptune, under millions of times Earth's pressure, it becomes a conductive fluid capable of bending magnetic fields into strange shapes. Picture a giant, swirling vat of this exotic fluid, its motion uneven due to Neptune's internal heat flows, distorting the magnetic field like a funhouse mirror. What makes these tilted fields so important isn't just their strangeness, it's what they reveal about the universe's flexibility. Magnetic fields don't have to follow tidy textbook models. They can twist, warp, and even flip under the right conditions. And if we ever send probes to these ice giants like NASA proposed Uranus orbiter, we might finally glimpse the engines powering these cosmic anomalies. Until then, Uranus and Neptune remain a reminder. Even in our own backyard, the universe still has surprises tucked beneath its icy sleeves. Imagine snapping a rubber band stretched to its limit. That sudden release of pent-up energy is a tiny echo of what happens when cosmic magnetic fields break and reconnect. This explosive process, called magnetic reconnection, is nature's ultimate power switch, capable of transforming invisible magnetic tension into raging storms of energy. From the shimmering curtains of Earth's auroras to the violent eruptions on the Sun's surface, this phenomenon shapes some of the most dazzling and destructive events in the universe. And the most astonishing part, we're only now learning how to read its chaotic choreography. Take a solar flare. A single one can unleash energy equivalent to 1 billion hydrogen bombs in mere minutes. At the heart of this cataclysm, magnetic field lines near the Sun's surface stretch, tangle, and finally snap like overburdened cables. When they reconnect, the energy stored in those twisted fields explodes outward, accelerating particles to nearly light speed and heating plasma to millions of degrees. The same process, scaled down, creates the northern lights. Earth's magnetic field captures solar wind particles, funneling them toward the poles where field lines reconnect, releasing energy that paints the sky with ethereal glow. But the real frontier lies in the extremes. Near black holes and neutron stars, magnetic reconnection reaches almost unimaginable scales. The Event Horizon Telescope's images of Galaxy M87 revealed jets of plasma stretching thousands of light years, likely powered by reconnection events near the black hole's event horizon. Here, magnetic fields don't just snap, they writhe like living things, channeling enough energy to hurl superheated gas across cosmic distances. NASA's Magnetospheric Multiscale Mission, or MMS, has brought this cosmic puzzle into focus. By flying 4 spacecraft in tight formation through Earth's magnetosphere, MMS has caught reconnection in action down to the electron scale. What it found defied expectations. Instead of a slow, steady process, reconnection happens in explosive bursts, with magnetic fields breaking and reforming in mere seconds. These observations are rewriting textbooks, revealing how energy transfers from fields to particles in ways we never predicted. The implications stretch beyond astrophysics. If we could harness controlled magnetic reconnection here on Earth, it might revolutionize fusion energy. Tokamak's donut-shaped fusion reactors struggle with instabilities caused by rogue magnetic fields. But if we could trigger and direct reconnection like a cosmic lightning rod, we might finally tame plasma's chaos, unlocking near limitless clean energy. Labs worldwide are already testing the idea, using powerful lasers to recreate miniature versions of solar flares in controlled settings. Yet for all our progress, magnetic reconnection remains a puzzle wrapped in plasma. Why do some events release energy smoothly while others detonate like bombs? How do particles get accelerated to such incredible speeds? Each answer peels back another layer of this universal process, one that connects the flicker of auroras to the fury of quasars, proving once again that magnetism writes the universe's most dramatic scripts in lines of invisible force. Deep in the cosmic shadows, where the universe hides its greatest secret, dark matter exerts its invisible grip on galaxies. But could this mysterious substance also leave fingerprints on magnetism? The idea seems almost paradoxical. Dark matter famously refuses to interact with light or electromagnetic forces, yet some daring theories suggest it might have a hidden magnetic side, subtly warping the fields that shape galaxies in ways we're only beginning to imagine. One provocative possibility is that dark matter isn't entirely dark in the magnetic sense. A fraction of these elusive particles might carry what's called a millicharge, a sliver of an electron's charge, so tiny it's evaded detection. If true, these particles could nudge magnetic fields as they drift through galaxies, like invisible hands brushing against cosmic compass needles. The effect would be vanishingly small, but over billions of years, even a whisper of influence could leave a detectable mark. The challenge, spotting it, requires sifting through galactic magnetism with precision finer than a cosmic scalpel. Then there's the gravitational angle. Dark matter's sheer mass bends spacetime, sculpting galaxies into their familiar shapes, and where matter flows, magnetic fields often follow. Picture a vast river of dark matter pulling stars and gas along its gravitational currents. Those movements could stretch and twist galactic magnetic fields like taffy, imprinting patterns that reflect dark matter's hidden architecture. Some astronomers are already hunting for these ghostly signatures, mapping distortions in magnetic fields that can't be explained by visible matter alone. The stakes couldn't be higher. If dark matter and magnetism are entangled, it would rewrite the rules of particle physics. Current detectors like the Alpha Magnetic Spectrometer on the International Space Station are scanning cosmic rays for anomalies that might betray dark matter's electromagnetic flirtations. Meanwhile, radio telescopes peer into galaxy clusters, searching for magnetic distortions that align with dark matter's gravitational shadow. A single definitive detection could crack open two of cosmology's toughest puzzles at once. Yet the universe loves a good paradox. If dark matter does shape magnetism, why haven't we seen clearer evidence? Perhaps the effect is too faint, buried in noise. Or maybe dark matter's magnetic role is indirect, a cosmic game of telephone where gravity does the talking. Either way, every null result tightens the noose around these theories, forcing physicists to think even wilder thoughts. Could dark matter's magnetism be fleeting, flickering into existence only under extreme conditions? Or might it require entirely new forces beyond our current models? What's certain is this: the intersection of dark matter and magnetism is where the known universe brushes against the unknown. Every unexplained wiggle in a galactic field, every anomalous particle detection could be a clue or a red herring. But in this high-stakes game of cosmic hide and seek, even failure teaches us something profound: that the universe's greatest secrets are often hidden not in the light, but in the delicate interplay between shadow and force. Brown dwarfs are cosmic misfits, too massive to be planets, yet too puny to ignite as full-fledged stars. These dim, drifting bodies were long thought to be little more than lukewarm afterthoughts in the stellar catalogue. But recent discoveries have revealed a stunning secret. Despite their failed star status, brown dwarfs boast magnetic fields that put some active stars to shame, crackling with auroras that light up their skies without any nearby star to power them. How can objects barely hotter than a campfire generate magnetic storms rivaling Jupiter's? The answer might lie in the bizarre quantum dances happening deep inside their cores. Take the brown dwarf LSRJ 1835 plus 359, a lonely wanderer drifting just 30 light-years away. When astronomers pointed radio telescopes toward it, they detected a magnetic field over 200 times stronger than Jupiter's, far too intense for conventional models to explain. Normally, magnetic dynamos require churning layers of conductive fluid, like Earth's molten iron core or the Sun's plasma oceans. But brown dwarfs are stuck in a twilight zone, too cool for full-scale nuclear fusion, yet dense enough to crush hydrogen into exotic states. Some researchers suspect their magnetism springs from electron-degenerate hydrogen, a form of matter where atoms get squeezed so tightly, electrons break free and flow like a metallic fluid. Picture the core of a brown dwarf as a seething, superconducting sponge, where quantum effects amplify even the faintest motions into planet-scale magnetic fields. Then there's the aurora puzzle. On Earth, the northern lights flare when solar wind particles collide with our magnetic field. But brown dwarfs like WISE J0855-0714, floating in the abyss far from any star, somehow produce auroras just as vivid. Without a stellar wind to ignite them, what's sparking these light shows? One theory points to volcanic moons. Imagine a Jupiter-sized brown dwarf orbited by a hyperactive Io-like satellite, spewing charged particles into its magnetic embrace. Alternatively, the dwarfs themselves might be ejecting plasma through violent weather systems, their ultra-strong fields whipping up storms that rain electrons back onto their atmospheres. The James Webb Space Telescope is now hunting for answers, analyzing the infrared glow of brown dwarf atmospheres for chemical traces of these magnetic tantrums. Early data reveals possible auroral footprints, unexpected spikes in ionized hydrogen and helium that shouldn't exist without fierce magnetic activity. Some spectra even hint at swirling polar vortices, where charged particles spiral downward in glowing funnels. What's emerging is a portrait of brown dwarfs as cosmic electromagnets with a flair for drama. Their existence challenges our definitions of planets and stars, proving that magnetism doesn't play by the same rules across the universe. And as JWST peers deeper into their turbulent skies, we might find these failed stars are hiding the keys to magnetic phenomena we've never dreamed possible, ones that could rewrite the book on how cosmic dynamos work, from the smallest rogue worlds to the mightiest stars. The solar wind isn't just a gentle breeze, it's a hurricane of charged particles, screaming through space at 1,000,000 miles per hour while dragging the sun's twisted magnetic fields along for the ride. Close to Earth, we see this chaos tamed into shimmering auroras, where the solar wind tangles gracefully with our planet's magnetic shield. But venture farther out beyond the moon's orbit, and the true nature of this cosmic gale reveals itself. A churning sea of magnetic turbulence, where invisible whirlpools and shockwaves ripple across the solar system with enough force to scramble spacecraft electronics or fry unprotected astronauts. Picture the solar wind not as a smooth river, but as whitewater rapids. As it races away from the sun, the wind carries loops and kinks in its magnetic field like a garden hose flailing violently after being turned on full blast. These magnetic wrinkles grow more pronounced over distance, colliding and breaking into fractal patterns that resemble storm clouds on Jupiter. Near Mars, where Earth's protective magnetosphere no longer shields us, this turbulence becomes a genuine hazard. NASA's MAVEN orbiter has detected magnetic twisters in the solar wind near Mars, sudden reversals in field direction that could induce dangerous currents in any future human habitat. The real mystery isn't just the turbulence itself, but what drives it. Some shocks stem from coronal mass ejections, the sun's tantrums that hurl billion-ton plasma clouds into space. Others emerge spontaneously as fast and slow solar wind streams crash into each other, like cosmic traffic jams generating magnetic potholes. The most puzzling are the switchbacks, bizarre S-shaped kinks in the magnetic field first spotted by the Parker Solar Probe. These whip-like flips happen so abruptly, they reverse the solar wind's magnetic polarity in seconds, accelerating particles to dangerous energies. Some scientists think they're caused by magnetic reconnection near the sun's surface. Others argue they're remnants of explosive plasma jets from deep inside the corona. Untangling this mess isn't just academic. Every flicker in the solar wind's magnetic field carries consequences. During Apollo missions, astronauts reported seeing light flashes, even with eyes closed, now known to be cosmic rays deflected by Earth's magnetosphere but unimpeded in deep space. Future Mars travelers won't have that protection. A single powerful shockwave in the solar wind could bathe their ship in radiation equivalent to a year's worth of X-rays. That's why missions like ESA's Solar Orbiter are mapping this turbulence in 3D, hoping to predict when and where these invisible storms will strike. Perhaps the most fascinating twist is how this chaos might shape other worlds. Venus, lacking a global magnetic field, has its atmosphere slowly sandblasted away by the solar wind's turbulence. Mars suffered the same fate over billions of years, its once thick air stripped down to a wisp. Even icy moons like Jupiter's Europa feel the effects, their surfaces scarred by particle bombardments redirected by magnetic whirlpools. The solar wind's turbulence isn't just a local phenomenon, it's a sculptor of planetary destinies, etching its signature across the solar system one magnetic knot at a time. As we prepare to send humans beyond Earth's magnetic embrace, cracking this puzzle becomes existential. Will we learn to navigate the solar wind's invisible rapids, or be at the mercy of its capricious currents? The answer lies in decoding the sun's magnetic whispers, a language of storms written in the fabric of space itself. Mercury shouldn't have a magnetic field at all. At least, that's what conventional planetary science would predict. This tiny world, barely larger than Earth's moon, has no business hosting an active global magnetic shield, yet there it is, faint but undeniable, flickering like a candle in the solar wind's relentless gale. The mystery isn't just why Mercury's field exists, but why it's so bizarrely weak, 100 times feebler than Earth, yet still dynamic enough to create miniature auroras and whip up magnetic tornadoes in its thin exosphere. The answer might lie in a core unlike anything else in our solar system, where molten iron dances with an unexpected partner, sulfur. When NASA's Messenger probe first mapped Mercury's magnetism in 2011, scientists expected to find a relic field frozen into the planet's crust, a fossil of ancient dynamo activity long gone silent. Instead, they discovered a field that was alive, patchy, asymmetrical, and strangely offset northward, as if Mercury's magnetic heart was beating off rhythm. The most plausible explanation, a partially molten core still churning sluggishly after 4.5 billion years. But here's the twist: Mercury's core should have cooled solid eons ago. Its small size means heat escapes easily, like a baked potato cooling faster than a Thanksgiving turkey, unless something was keeping that core warm. That's where sulfur enters the stage. Earth's core is mostly iron and nickel, but Mercury's might be laced with lighter elements like sulfur, which lower its melting point. Picture a snow globe where the flakes are iron crystals, suspended in a sulfur-rich slurry. This sloshy mixture could keep Mercury's dynamo limping along, generating just enough magnetic field to cling to existence. Messenger gravity measurements support this idea, revealing a core so abnormally large it occupies nearly 85% of the planet's radius, with a solid outer shell encasing a molten inner layer. It's as if Mercury's core is a Russian nesting doll of magnetic oddities, yet the plot thickens. Mercury's field isn't just weak, it's also full of holes. The solar wind pummels its surface so intensely that magnetic cracks form, allowing charged particles to rain down and kick up sodium atoms from the soil in eerie, comet-like tails. During particularly violent solar storms, these breaches can stretch halfway to the planet's equator, like cosmic wounds bleeding atmosphere into space. And somehow, against all odds, Mercury's field persists, rebuilding itself like a cosmic phoenix. What makes this puzzle so revolutionary isn't just the science, it's the implications. If a tiny, sulfur-soaked core can sustain even a feeble magnetic field, then countless exoplanets once written off as lifeless might harbor hidden dynamos of their own. Worlds smaller than Earth, orbiting close to their stars, could be far more magnetically active than we ever imagined. Mercury stands as a testament to the universe's creativity, proof that when it comes to magnetism, even the rules we think are set in stone might just bend. Detecting magnetic fields on distant exoplanets might sound like hunting for ghosts with a flashlight, but this cosmic detective work could reveal which worlds beyond our solar system harbor the secret ingredient for life. While we've discovered thousands of planets orbiting other stars, their magnetic shields remain invisible to traditional telescopes. Yet without this protective barrier, even the most Earth-like exoplanet could be a radiation-blasted wasteland. So how do we spot something as intangible as a magnetic field from light years away? Astronomers are getting creative, chasing faint radio whispers and atmospheric fingerprints that betray these hidden forces. Take the case of TRAPPIST-1e, a rocky world in its star's habitable zone. On paper, it's a prime candidate for alien oceans, but without a magnetic field, its atmosphere would be slowly shredded by stellar winds, just like Mars. To probe this mystery, scientists listen for low-frequency radio bursts. When a planet's magnetic field interacts with its star's charged particles, it can emit cyclic radio waves, a cosmic distress signal revealing the field's presence. In our solar system, Jupiter's auroras blast out such signals so powerfully, they're detectable across interstellar distances. The problem: exoplanet magnetic fields are likely thousands of times weaker. Current telescopes like LOFAR strain to catch these faint pulses, but next-generation arrays like the Square Kilometre Array could finally tune in. Atmospheres tell another part of the story. A world like GJ 1132b, whose hydrogen-rich envelope persists despite being bombarded by its red dwarf star, might owe its survival to a magnetic shield deflecting stellar assaults. Conversely, the evaporating atmosphere of HD 209,458b, a gas giant trailing a comet-like tail, could signal a missing or faltering magnetic defense. The James Webb Space Telescope is now analyzing such atmospheric escape rates, using them as indirect barometers for exoplanetary magnetism. The stakes go beyond academic curiosity. Magnetic fields don't just block radiation, they prevent stellar winds from stripping away water vapor, a prerequisite for stable oceans. Europa and Enceladus show that subsurface liquid can exist without a thick atmosphere, but complex life likely needs both. Future telescopes like the Habitable Worlds Observatory aim to spot magnetic footprints in exoplanet auroras or polarized starlight bending around magnetospheres. What keeps this search electrifying is the sheer diversity of possibilities. Imagine a super-Earth with a molten core churning faster than Earth's, generating a magnetic field strong enough to shield continents from hyperactive flare stars. Or a tidally locked planet where magnetism focuses auroras into a permanent spotlight on its dark side. Each discovery could rewrite our understanding of planetary habitability, proving that magnetism isn't just a detail in the story of life, but possibly its most crucial plot twist. Every magnet you've ever held, from fridge decorations to compass needles, has an inescapable duality, a North Pole and a South Pole, inseparable no matter how many times you break it in half. But what if the universe played by different rules in its infancy? Hidden in the equations of particle physics lies a tantalizing possibility: magnetic monopoles, hypothetical particles that carry just a single pole, either north or south, floating freely through space like cosmic misfits. These elusive entities aren't just scientific curiosities. They could hold the key to unlocking some of the universe's deepest symmetries, rewriting textbooks from the ground up. The hunt for monopoles traces back to a glaring asymmetry in James Clerk Maxwell's equations, the foundational laws of electromagnetism. While electric charges, positive and negative, exist independently, magnetism stubbornly refuses to follow suit. Yet certain grand unified theories, which attempt to merge electromagnetism with the strong and weak nuclear forces, predict that monopoles should have been forged in the unimaginable heat of the early universe. Picture the cosmos a fraction of a second after the Big Bang, a seething cauldron of energy where fundamental forces hadn't yet split apart. In that chaos, topological defects in spacetime itself could have frozen into existence like cracks in ice, birthing particles with isolated magnetic charges. For decades, physicists have scoured the universe for traces of these relics. Some experiments have hunted for monopoles trapped in ancient minerals, their passage leaving ghostly trails in mica or olivine crystals over billions of years. Others have turned particle colliders into monopole factories, slamming protons together at near light speeds in hopes of recreating those primordial conditions. The most dramatic search unfolded in the 1980s, when physicist Blas Cabrera's ultra-sensitive superconducting loop recorded a single, abrupt current spike, exactly what a passing monopole's magnetic flux would produce. The scientific world held its breath, but the event never repeated, leaving the detection shrouded in mystery. What makes monopoles so revolutionary isn't just their defiance of everyday magnetism. Their existence could explain cosmic inflation, the universe's explosive expansion in its first moments. According to some theories, monopoles would have been so absurdly abundant early on that their gravitational influence should have collapsed the cosmos, unless something like inflation diluted them to near invisibility. Finding even one would prove this scenario correct, effectively turning a monopole into a time capsule from the universe's first trillionth of a second. Yet the silence so far has spurred wild alternatives. Could monopoles be hiding in plain sight, masquerading as dark matter? Some models suggest certain dark matter particles might carry fractional magnetic charges, evading detection by conventional means. Or perhaps they're not particles at all, but sprawling cosmic strings, filaments of energy left over from the Big Bang, that act like monopoles when viewed from a distance. The longer the search continues, the more creative the theories become. One thing's certain: if monopoles are ever found, they won't just fill a gap in our equations. They'll tear open a new chapter in physics, revealing a universe far stranger and more symmetrical than we ever imagined. Until then, they remain one of cosmology's most tantalizing what-ifs, a whisper from the dawn of time, waiting to be heard. Pulsars are nature's most precise clocks, spinning neutron stars that beam radiation across the cosmos with a rhythm so steady, they rival atomic timekeepers on Earth. But even these cosmic metronomes aren't perfect. Occasionally, their ticking stutters. A pulse arrives a fraction of a second early or late, betraying hidden turmoil beneath their gleaming surfaces. And here's the twist. These tiny hiccups aren't flaws in the universe's timing, they're clues, etched in magnetism, that reveal secrets about everything from the bizarre physics inside neutron stars to the fabric of spacetime itself. At the heart of every pulsar lies a magnetic field so intense, it bends the very radiation it emits into focused beams. As the star spins, these beams sweep past Earth like a lighthouse, creating the pulses we detect. But that magnetic field isn't static. It's tangled in a dance with the pulsar's interior, where a superfluid ocean of neutrons swirls frictionlessly, like liquid helium on a cosmic scale. When this superfluid suddenly unpins from the star's crust, think of ice cracking on a frozen lake. It transfers angular momentum in a violent jerk, causing the pulsar to spin faster for a split second. The result, a glitch. These events, smaller than a millisecond but detectable with radio telescopes, are like cosmic telegrams, carrying details about conditions we could never probe directly. What makes these glitches revolutionary isn't just their cause, it's their consequences. By tracking pulsar timing with nanosecond precision, astronomers have turned these stars into laboratories for extreme physics. Take the double pulsar system PSR J07373039, where two neutron stars orbit each other at breakneck speed. Their magnetic interactions create timing variations so slight, they've become one of the most stringent tests of Einstein's general relativity. Every deviation from predicted pulse arrivals either confirms the theory or, more tantalizingly, hints at where it might break down. But the real frontier lies in gravitational wave detection. When ripples in spacetime pass through our galaxy, they stretch and compress the distances between pulsars and Earth, altering the arrival times of their pulses in a telltale pattern. By monitoring arrays of pulsars, a technique called a pulsar timing array, scientists have begun sensing these waves from monstrous black hole mergers far beyond our local universe. And here's where magnetism adds another layer. The same magnetic fields causing glitches also influence how pulsars slow down over time, meaning understanding their quirks is essential to filtering out noise and isolating the whisper of gravitational waves. The beauty of pulsar timing lies in its duality. These stars are both victims and tools of their own magnetic chaos. A glitch might disrupt their rhythm, but that disruption becomes a window into superfluid dynamics, a test of relativity, and a gravitational wave detector, all at once. And as radio telescopes grow more sensitive, we're not just listening to pulsars, we're decoding a language of magnetic turbulence that speaks volumes about the universe's most hidden workings. Every stutter, every hiccup is a sentence in a story written in spacetime and magnetism, one we're only beginning to read. Among the moon's stark gray plains, strange bright swirls curl across the surface like cosmic fingerprints, luminous patterns that defy easy explanation. The most famous, Reconnection Gamma, stretches over 40 miles in a glowing, tadpole-shaped streak, visible even through backyard telescopes. But what makes these swirls truly puzzling isn't just their appearance, it's their eerie alignment with localized magnetic fields, patches of lunar crust that somehow retained magnetism billions of years after the moon's global field faded. How do these ghostly fields persist, and could their secrets make the moon safer for future astronauts? One leading theory points to ancient violence, cometary impacts that struck the moon with enough force to magnetize the ground. Picture a colossal comet slamming into the lunar surface, its icy core vaporizing instantly in the heat of collision. The explosion would have generated a superheated plasma cloud, charged particles swirling in a temporary magnetic maelstrom. As this chaos settled, the shockwave could have imprinted a magnetic signature onto the surrounding rock, like a cosmic stamp pressed into molten metal. Supporting this idea, some swirls sit at the edges of impact basins where comets likely struck, and laboratory experiments show that simulating such high-energy impacts can magnetize lunar-like minerals in an instant. But there's a rival hypothesis lurking beneath the surface, literally. Beneath these swirls, the moon might hide underground rivers of frozen lava, remnants of volcanic activity that ended over 1 billion years ago. As this lava cooled, minerals like ilmenite, rich in iron and titanium, could have crystallized in the presence of a weak magnetic field, locking its direction into the rock like a fossilized compass. Over time, as the surrounding non-magnetic material eroded from micrometeorite bombardment, these magnetized patches would stand out, creating the swirls we see today. Lunar orbiter data adds weight to this idea, showing that some swirls overlap with ghostly remnants of ancient volcanic tubes. The implications go beyond lunar geology. If these magnetic anomalies are strong enough, they might form natural shields against the solar wind's relentless radiation, a potential lifeline for future lunar colonies. Earth's magnetic field deflects most harmful particles, but on the moon's unprotected surface, astronauts would face constant bombardment. A base built near Enigma or similar swirls could exploit these localized fields as makeshift radiation shelters, reducing exposure without costly artificial shielding. Early measurements suggest some swirl-associated fields are indeed deflecting solar particles, creating miniature safe zones just meters wide, tiny oases in a lethal environment. Yet mysteries remain. Why do some swirls glow brighter than others? Are their magnetic fields stable, or do they flicker over time? NASA's upcoming Lunar Vertex rover, set to land directly on Enigma, aims to answer these questions by mapping the swirl's magnetism in unprecedented detail. What it finds could rewrite our understanding of the moon's hidden dynamism and prove that even in its apparent stillness, the moon holds magnetic surprises waiting to be uncovered. For explorers of the future, these swirling enigmas might be more than just curiosities. They could be the key to calling the moon home. At the chaotic core of our galaxy, where stars whip around an invisible behemoth at speeds approaching light, magnetism isn't just present, it's the puppet master pulling the strings. Sagittarius, a star, the supermassive black hole anchoring the Milky Way, hides within a labyrinth of magnetic fields so intense they warp the very fabric of space around it. Recent images from the Event Horizon Telescope, the same collaboration that captured humanity's first black hole photo, reveal these fields as ghostly threads, swirling in eerie patterns near the event horizon like cosmic spider silk. But these aren't passive decorations. They're active players in one of the universe's most violent ballets, directing the flow of doomed gas and shaping the fates of entire star systems. Picture the scene, a river of interstellar material spiraling toward the black hole's maw, accelerated to relativistic speeds. Without magnetism, this gas would plunge into oblivion in a chaotic free-for-all. Instead, the fields act like celestial traffic cops, organizing the chaos into orderly lanes. Some particles get funneled into jets, twin beams of plasma shooting outward at nearly light speed, stretching thousands of light years into space. Others are whipped into frenzied orbits, their friction generating X-rays bright enough to outshine every star in the galaxy combined. The EHT's polarized light images show these fields aren't random. They form coherent structures, with some regions resembling the perfectly combed lines of a cosmic haircut, while others twist into helical coils tighter than DNA. What's truly baffling is how these fields withstand the black hole's gravitational shredding. Near the event horizon, tidal forces should tear magnetism apart like tissue paper, yet somehow the fields persist, even strengthening in certain zones. One theory suggests the black hole's rotation acts like a dynamo, twisting space-time itself into a magnetic amplifier. As the black hole spins, it drags the fabric of reality around it, winding up magnetic field lines until they snap with the energy of a trillion supernova. These eruptions might explain the mysterious flares observed near Sagittarius, a star sudden bursts of radiation that light up the galactic center like a cosmic strobe. The implications stretch far beyond our galaxy's core. These magnetic structures could solve a long-standing paradox: why some supermassive black holes feast voraciously while others starve. Fields too strong might choke off accretion, acting like a cosmic valve, while weaker ones allow gas to flood in unimpeded. This delicate balance might determine whether a black hole powers brilliant quasars or lurks in darkness, and by extension, whether its host galaxy becomes a stellar factory or a cosmic graveyard. As astronomers refine the EHT's observations, they're glimpsing something even more profound: hints that these magnetic fields might encode the black hole's history like rings in a tree trunk. The direction of their twists could reveal past mergers where smaller black holes spiraled into Sagittarius, a star, imprinting their spin on its magnetic fingerprint. It's as if the universe left a forensic trail in lines of force one were just learning to read. Every new observation peels back another layer, revealing that even in the darkest heart of the galaxy, magnetism writes the rules. Beyond the planets, beyond the Kuiper belt, even beyond the reach of sunlight, the Voyager probe stumbled upon something utterly unexpected: a frothy sea of magnetic bubbles, each one tens of millions of miles wide, churning at the edge of our solar system. This isn't the smooth, orderly boundary scientists once imagined. It's a turbulent frontier where the sun's magnetic field fractures into a labyrinth of floating pockets, like cosmic soap suds adrift in the void. The discovery rewrote our understanding of the heliosphere, that protective bubble carved out by the solar wind, and raised a tantalizing question: if our sun creates this magnetic foam, what strange structures might lurk around other stars? The key to these bubbles lies in a process called magnetic reconnection, where the sun's field lines stretch, snap, and reconnect in explosive tangles. Near Earth, we see this in solar flares, but at the solar system's edge, the rules change. Here, the solar wind slows abruptly as it collides with interstellar space, piling up like traffic at a cosmic toll booth. The magnetic field, no longer streamlined by the wind's flow, crumples into a chaotic froth. Voyager's instruments revealed this mess firsthand, detecting sudden spikes and drops in magnetic strength as the probes punched through one bubble after another, like ships navigating a floating minefield. What's wild is how these bubbles might act as cosmic ray traps. High-energy particles from distant supernova, which would normally bombard the inner solar system, could get tangled in this magnetic foam, bouncing from bubble to bubble like pinballs. Some might leak inward slowly, while others are deflected entirely. This could explain why cosmic ray levels fluctuate so mysteriously at the solar system's edge, and why Earth experiences fewer of these deadly particles than expected. If the heliosphere's bubbly fringe is our first line of defense, it's a far weirder shield than anyone predicted. Now imagine scaling this up around other stars, especially those with stronger winds or faster rotation. These magnetic bubbles could be even more extreme. A young, hyperactive star might generate a heliosphere so frothy it resembles a sponge with cosmic rays filtering through labyrinthine gaps. Meanwhile, a sluggish red dwarf's bubbles could be sparse and fragile, offering little protection to any orbiting planets. Future telescopes, like the Interstellar Mapping and Acceleration Probe, aim to map these structures remotely by analyzing how starlight polarizes as it passes through their magnetic chaos. The deeper mystery: these bubbles might not be unique to stars. Galaxies themselves could harbor similar magnetic foam at their edges, where galactic winds collide with the near-nothingness of intergalactic space. If so, the entire cosmos could be filled with these invisible, frothy boundaries shaping how energy, particles, and even magnetic fields themselves travel across the universe. Voyager gave us the first glimpse of this hidden architecture, but the real revelation is how much we still have left to explore, one magnetic bubble at a time. In the swirling chaos of a young star's birth, where dust and gas collide in a frenzied dance, an invisible hand is quietly shaping the destiny of worlds. Protoplanetary disks, those vast, pancake-shaped nurseries where planets are born, aren't just passive collections of debris. They're dynamic arenas where magnetic fields twist and surge, orchestrating the assembly of everything from pebbles to gas giants. The Atacama Large Millimeter Array, or ALMA, has pierced through the dust to reveal these hidden forces, capturing snapshots of magnetic lines weaving through disks like cosmic blueprints. What they've found challenges everything we thought we knew about planet formation. Take HL Tau, a star just 1 million years old, whose disk ALMA imaged in stunning detail. The magnetic fields here aren't random. They're aligned in concentric rings like grooves on a vinyl record. This structure isn't decorative, it's functional. Dust grains, which would normally bounce off each other like billiard balls, instead find themselves guided by these magnetic lanes, gently nudged into collisions sticky enough to build planetesimals, the seeds of future worlds. Without magnetism, the disk might remain a featureless cloud, its material forever too scattered to coalesce. But with these fields acting as invisible scaffolding, chaos gives way to order and planets get a head start. Yet not all disks follow the same magnetic script. Some, like IM Lup, showcase fields that spiral inward like whirlpools, funneling material toward the star at breakneck speeds. Others, like TW Hydri, exhibit more turbulent fields where patches of magnetism resemble tangled yarn. This diversity might hold the key to why some systems end up with close orbiting super-Earths while others spawn distant gas giants. In strongly magnetized disks, gas gets dragged inward faster, leaving behind a dust-rich outer region where rocky worlds can form in peace. Meanwhile, weaker fields might allow gas to linger, creating the perfect conditions for Jupiter-like behemoths to take shape. The real surprise: these fields might even solve the mystery of misaligned planets' worlds orbiting at bizarre angles to their star's equator. ALMA images of HD 143006 show a disk warped like a vinyl record left in the sun, its magnetic fields bent by gravitational interactions with nearby stars. Planets forming here would inherit this tilt, destined for orbits that defy expectations. It's a reminder that magnetism doesn't just build planets, it imprints them with the history of their birth, like a cosmic fingerprint. As we peer deeper into these planetary cradles, one truth becomes clear: magnetism isn't just a side character in the story of planet formation. It's the director, choreographing the motions of dust and gas with a precision that rivals the finest machinery. And with every new disk ALMA unveils, we're decoding the hidden language of forces that shaped not just our solar system, but countless others across the cosmos. The next time you look up at the night sky, remember the planets you see might owe their very existence to the silent, invisible pull of magnetic fields, written into the fabric of space long before their worlds were born. Deep in the void between stars, cosmic rays scream through space at nearly light speed. Subatomic bullets fired from supernova black holes and other cosmic monsters. But some of these particles carry an enigma stamped in their energy signatures. They're too slow, too abundant, or moving in directions that defy expectations. These misfits, dubbed anomalous cosmic rays, might seem like mere outliers until you realize their odd behavior could be a cipher, one that reveals the Milky Way's hidden magnetic skeleton. The mystery starts close to home, when spacecraft like NASA, Voyager, and IBEX probed the edge of our solar system. They found cosmic rays with energies oddly depleted, like marathon runners who'd inexplicably slowed to a stroll. The leading theory: these particles aren't interstellar invaders at all, but homegrown. Neutral atoms drifting into the heliosphere get ionized by sunlight, snatched up by the solar wind, and hurled back outward, only to collide with the heliosphere's magnetic boundary, where they're accelerated anew. Think of it as a cosmic pinball machine. Particles ricochet off magnetic shock fronts, gaining just enough energy to appear anomalous when they loop back inward. Yet the plot thickens beyond our solar bubble. Some high-energy cosmic rays arrive at Earth with trajectories so skewed, they must have been deflected by interstellar magnetic fields we've yet to map. Here's where these oddballs become cosmic cartographers. Charged particles spiral along magnetic field lines like beads on a wire, their paths bending in ways that betray the strength and orientation of the fields they've traversed. By tracing these detours, scientists are reverse engineering the Milky Way's magnetic web, a structure otherwise nearly invisible. Already, anomalies in cosmic ray distributions hint at vast, magnetized filaments stretching hundreds of light years, possibly remnants of ancient supernova shocks or galactic-scale plasma currents. The real breakthrough may come from combining these clues with polarized starlight. When light passes through magnetized space, its waves align in telltale patterns, a phenomenon that's helped trace fields near star-forming regions. But cosmic rays probe deeper, sampling magnetism in the barren voids between stars where traditional methods go blind. Future observatories like the Cherenkov telescope array aim to cross-reference these datasets, piecing together a 3D magnetic atlas of our galaxy. What's at stake isn't just academic. These invisible fields sculpt galactic ecosystems, guiding star formation and shielding planetary systems from lethal radiation. Unraveling their structure could answer why some regions of the Milky Way sparkle with young stars while others languish as cosmic deserts. And for astronauts venturing beyond Earth's shield, understanding these magnetic byways might one day mean the difference between a safe journey and a lethal radiation bath. So while anomalous cosmic rays might seem like backwater curiosities, they're really messengers whispering secrets about the forces that shape everything from the smallest particle to the grandest spiral arm. During the Apollo missions, astronauts orbiting the Moon reported something eerie, a faint glow hovering just above the lunar horizon, like an otherworldly sunrise in the middle of the lunar night. This wasn't sunlight scattering or camera artifacts. It was a real phenomenon, one that flickered unpredictably and vanished as mysteriously as it appeared. Decades later, we're still piecing together the puzzle of these transient lunar glows, and the answer might lie in the Moon's ghostly, fragmented magnetic fields interacting with the solar wind in ways we never anticipated. Unlike Earth's global magnetic shield, the Moon's magnetism is patchy, scattered across its surface in isolated bubbles, remnants of a dynamo that died billions of years ago. But these fields aren't entirely dormant. When the solar wind, a stream of charged particles from the sun, slams into these magnetic anomalies, something extraordinary happens. Electrons trapped in the fields get funneled downward, striking the lunar soil and kicking up microscopic dust grains. These particles, now electrically charged, levitate just above the surface, scattering sunlight into that elusive horizon glow. It's as if the moon, long thought to be geologically dead, still breathes in magnetic whispers, exhaling fleeting auroras visible only to those who know where to look. The strangest part, these events might not be unique to our moon. Airless worlds across the cosmos, from Mercury to distant exoplanets, could harbor similar magnetic ghosts. Imagine a tidally locked exoplanet, its dayside scorched by its star, while its nightside flickers with sporadic glows from residual magnetism interacting with stellar winds. Future telescopes like the Habitable Worlds Observatory might spot these transient signatures, hinting at magnetic activity on worlds too small or cold for traditional dynamos. Artemis missions aim to solve this riddle firsthand. NASA's Lunar Vertex rover, slated to explore the Reconnection gamma magnetic anomaly, will map these fields with unprecedented precision, while astronauts could witness horizon glows in real time. What they uncover won't just rewrite lunar science, it might reveal magnetism's hidden role in shaping the atmospheres or lack thereof of countless worlds. After all, if a barren rock like the moon can still conjure ethereal light shows, what other magnetic surprises might the universe be hiding? Beneath Europa's cracked, icy shell lies an ocean darker than midnight, a vast, salty sea kept liquid by the relentless gravitational kneading of Jupiter. But this hidden world doesn't just slosh in silence. It hums with an electromagnetic whisper, a weak but detectable magnetic field that betrays its presence to passing spacecraft. Unlike Earth's internally generated field, Europa's is an induced one, a cosmic echo created as Jupiter's monstrous magnetosphere sweeps over the moon, electrifying its subsurface ocean like a planetary-scale battery. The Galileo probe first caught this signal in the 1990s, revealing not just the ocean's existence, but its startling conductivity, a clue that Europa's waters might be as salty as Earth's dead seas, laced with chlorides and sulfates that could nurture life. What makes this magnetic fingerprint so revolutionary is what it reveals about the ocean's structure. By measuring how the field fluctuates as Europa orbits Jupiter, scientists have estimated the ocean's depth, some 40 to 100 miles beneath the ice, and even detected plumes of water vapor erupting through fractures, tasting the chemistry of this alien sea from afar. The field's strength suggests the water isn't pure. It's a briny soup, possibly rich in magnesium sulfate or sodium chloride, electrolytes that could create conditions ripe for hydrothermal vents like those on Earth's ocean floor, where life thrives without sunlight. Now imagine scaling this discovery to the cosmos. If a faint magnetic signature can unveil an ocean on Europa, could the same trick work for exomoons orbiting distant gas giants? The James Webb Space Telescope is already hunting for water vapor in exoplanet atmospheres, but detecting induced magnetic fields around moons would require next-gen instruments like the proposed Europa Clipper's magnetometer, scaled to interstellar distances. A promising target, moons circling cold Jupiter's inhabitable zones, where tidal heating could maintain liquid water just as Jupiter does for Europa. Spotting their magnetic whispers would be like finding needles in a cosmic haystack, but the payoff would be staggering proof that habitable oceans aren't confined to planets. Yet Europa's field holds darker secrets too. Jupiter's radiation belts bombard its surface with lethal intensity, enough to kill an unshielded astronaut in hours. The induced magnetism offers no protection. Instead, it funnels charged particles toward the moon's poles, where they stain the ice with brownish scars of sulfur and organic compounds. For any hypothetical Europan life, this radiation would be an existential threat unless it's buried deep beneath the ice, sheltered in hydrothermal oases. Future missions like NASA Europa Clipper aim to map these radiation hotspots, plotting safe corridors for landers while searching for chemical traces of biology in plume ejecta. The grand irony: Europa's magnetic shield is both a beacon and a bullseye. It reveals the ocean that makes this moon one of the most promising places for life beyond Earth, yet it also channels the very radiation that makes its surface a wasteland. As we decode these magnetic clues, we're not just exploring a frozen moon, we're writing the playbook for how to hunt hidden oceans across the galaxy, one induced field at a time. White dwarfs are cosmic tombstones, the dense, Earth-sized cores left behind when stars like our Sun exhaust their nuclear fuel and quietly fade away. But some of these stellar remnants refuse to go gently into the night. Instead, they blaze with magnetic fields so intense they could erase a hard drive from halfway across the galaxy, while others sit in eerie magnetic silence. This stark divide presents one of the most perplexing puzzles in stellar evolution. How can two white dwarfs born from similar stars end up with such radically different magnetic legacies? Take Air Scorpii, a white dwarf pulsar that whips its companion star with beams of radiation like a cosmic lighthouse on overdrive. Its magnetic field clocks in at 500 million Gauss, nearly 100 million times stronger than Earth's. Then there's WD-0346+246, a nearby white dwarf whose field is so weak, it's virtually undetectable. This isn't just a minor discrepancy, it's a chasm, and the key to bridging it might lie in the violent moments before these stars took their final bow. One camp of astronomers argues these monstrous fields are heirlooms passed down from the stars that birthed them. As a sun-like star expands into a red giant, its core spins faster, like an ice skater pulling in their arms. If that star already had a modest magnetic field, this spin-up could amplify it through dynamo action, imprinting a powerful field onto the resulting white dwarf. Supporting this idea, some highly magnetic white dwarfs show unusual chemical abundances, hints that their progenitor stars might have been chemically peculiar AP/BP stars, known for their strong surface magnetism. But there's a plot twist. During the star's death throes, as it sheds its outer layers to become a planetary nebula, the remaining core undergoes a gravitational collapse so extreme it could forge magnetism anew. Picture this: the star's interior, compressed to densities where a sugar cube-sized chunk would weigh as much as an elephant, becomes a quantum playground. Electrons, packed shoulder to shoulder, form a degenerate gas where magnetic properties behave unlike anything in normal matter. Some theories suggest this environment could spontaneously generate ferromagnetic phases. Think of a gargantuan, spinning magnet locked inside a dying star's heart. The most tantalizing clue comes from white dwarf binaries. Systems like ReJ0317-853 show paired white dwarfs where one is highly magnetic and the other isn't, despite presumably forming under similar conditions. This dichotomy suggests something stochastic, like the chaotic alignment of magnetic domains during collapse, might determine a white dwarf's final magnetic state. It's as if the universe flips a coin during stellar death, heads for magnetism, tails for oblivion. What makes this puzzle so urgent isn't just academic curiosity. The interiors of these stars are laboratories for physics we can't recreate on Earth. At their cores, pressures are so extreme that carbon crystallizes into cosmic diamonds, while their magnetic fields could reveal new phases of matter that exist nowhere else. Future missions like ESA's Pluto might spot the gravitational waves from merging magnetic white dwarfs, letting us hear their interior structure for the first time. Every magnetic white dwarf is a Rosetta Stone, waiting to decode the secret language of stellar death. Whether their fields are relics or rebirths, Each one holds clues about the invisible forces that shape the cosmos and the strange quantum fates awaiting stars like our own. The universe's first magnetic fields might not have been forged in the fiery hearts of stars or the violent swirls of galaxies. They could be relics from the very dawn of time itself, imprinted onto the cosmos in the first fractions of a second after the Big Bang. Imagine a newborn universe, a seething plasma so hot and dense that even atoms couldn't yet exist. In that primordial chaos, quantum fluctuations, tiny, spontaneous ripples in the fabric of reality, might have twisted the soup of charged particles into the faintest magnetic whispers. These fledgling fields, weaker than a fridge magnet stretched across light years, could have been the seeds for every magnetic structure we see today. The beauty of this idea lies in its simplicity. Just as gravity amplified tiny density fluctuations into galaxies and galaxy clusters, the universe's expansion could have stretched these embryonic magnetic fields, transforming them from quantum hiccups into cosmic scaffolding. Early cosmic structures, vast filaments of gas condensing into the first protogalaxies, might have acted like natural dynamos, winding and amplifying these fields like a spinning turbine charges a battery. Over billions of years, this process could have woven magnetism into the very fabric of galactic evolution, explaining why even the most distant galaxies we observe already host organized magnetic fields. But how do we hunt for these cosmic fossils? Unlike dinosaur bones, primordial fields wouldn't leave behind physical remnants. Instead, astronomers search for indirect fingerprints. One clue lies in the cosmic microwave background, the afterglow of the Big Bang. If primordial fields existed, they would have subtly polarized this ancient light in telltale patterns, like invisible hands twisting the lens of a telescope. Experiments like the Simon's Array and future observatories such as CMB-S4 are scanning the sky for these faint magnetic imprints, hoping to spot the ghostly signature of the universe's first magnetism. Another approach probes the voids between galaxies. These near-empty regions, spanning hundreds of millions of light-years, are so pristine that any magnetism there can't be explained by stars or black holes. It must be primordial. Remarkably, radio telescopes have detected weak magnetic fields in these voids, their origins still debated. Could they be the faded echoes of those initial quantum twists, preserved like whispers in a cosmic cathedral? The implications are staggering. If primordial fields are real, they'd rewrite our understanding of cosmic evolution. Magnetic forces might have guided the collapse of the first gas clouds, shaping where and how stars ignited. They could even have influenced the large-scale structure of the universe, subtly steering matter into the web-like patterns we see today. And if these fields predate galaxies, they might solve a long-standing puzzle: why magnetism seems ubiquitous across the cosmos, even in places where conventional dynamo theories struggle to explain its presence. Yet the theory isn't without its skeptics. Some argue that turbulent plasma in the early universe would have shredded weak fields before they could amplify. Others propose alternative origins like magnetic batteries powered by temperature differences in ancient plasma. The debate rages on, but one thing's certain: whether relics of the Big Bang or later inventions, magnetic fields are more than cosmic afterthoughts. They're fundamental threads in the tapestry of the universe, woven into existence from its first breath to the present day. Unraveling their origins wouldn't just solve a puzzle, it would reveal how deeply magnetism is written into the story of everything. Saturn's magnetic field shouldn't be this well-behaved. While most planets, even Earth, sport fields tilted at odd angles, Saturn's aligns with eerie precision, its magnetic poles almost perfectly overlapping its geographic ones. This cosmic symmetry is so exact, it defies everything we know about how planetary dynamos work. Jupiter's field, for instance, tilts by about 10 degrees, and Earth's wobbles a full 11 degrees off kilter. But Saturn, a mere 0.06-degree slant, so slight it's like a spinning top balanced on a needle. So what's smoothing out Saturn's magnetic wrinkles? The answer might lie in the planet's deepest layers, where helium falls like rain through a sea of liquid metallic hydrogen. Picture this: deep inside Saturn, pressures rise so high that hydrogen, normally a gas, transforms into an electrically conductive fluid, swirling like molten metal. This churning layer powers the dynamo, generating the planet's magnetic field. But unlike Jupiter, Saturn's core might be wrapped in a blanket of helium droplets, condensing from the hydrogen soup above and sinking inward. As these droplets descend, they release heat, creating a stable, stratified layer that acts like a magnetic shock absorber. The result, a field so orderly, it's as if the cosmos ironed out all its kinks. The Cassini spacecraft gave us our first real clues. During its daring grand finale orbits, diving between Saturn and its rings, the probe measured the planet's gravity and magnetic field with unprecedented precision. The data revealed something startling. Saturn's dynamo might not operate deep in its core, as Earth's does, but in a vast shell of metallic hydrogen nearer the surface. This shallow dynamo, cushioned by that helium rain layer, could explain the field's uncanny alignment like a spinning top encased in syrup, its wobbles dampened before they ever reach the surface. Yet mysteries linger. If helium rain is the key, why doesn't Jupiter, a similarly gaseous giant, share this perfect symmetry? The difference might come down to mass. Saturn's lower gravity allows helium to condense and sink more uniformly, while Jupiter's intense heat and pressure keep its interior more turbulent. It's also possible Saturn's magnetic field isn't as stable as it seems. Some models suggest its alignment could be a fleeting phase, a cosmic coincidence in a billion-year cycle of magnetic reversals. The implications stretch beyond Saturn. Exoplanets with similar interiors might host equally precise fields, shaping their climates and even their potential for life. A well-aligned field could shield a planet's atmosphere more evenly, preventing the kind of polar erosion that left Mars barren. Meanwhile, Saturn's helium rain hints at hidden weather systems far beneath its clouds, storms not of wind and water, but of condensing elements and magnetic tides. As we unravel this puzzle, Saturn stands as a reminder. Even the most symmetrical phenomena in space often hide the wildest physics. Behind that perfect alignment lies a world where elements fall as rain, hydrogen flows like liquid metal, and magnetism dances to the tune of quantum forces we're only beginning to grasp. The next time you gaze at Saturn's serene rings, remember, the real drama is unfolding deep below, where the universe is quietly defying its own rules. We stand on the brink of a magnetic renaissance, where new tools and audacious ideas are transforming how we probe the universe's invisible forces. The Square-Kilometre Array, slated to begin full operations in the next decade, will map galactic magnetism with unprecedented resolution. Its thousands of antennas working in concert to trace field lines across millions of light-years. Meanwhile, facilities like the ITER fusion reactor are recreating stellar conditions in lab-sized chambers, allowing us to study how plasma and magnetism intertwine under extremes no telescope can directly observe. These instruments aren't just upgrades, they're portals to a hidden layer of cosmic reality. Consider how the SKA's polarized light observations could crack the primordial field mystery. By analyzing subtle twists in radio waves from the earliest galaxies, it might detect the faint imprint of magnetism dating back to the universe's first billion years, settling once and for all whether fields emerged with the Big Bang or were forged later by stars and black holes. Closer to home, lab experiments with laser-driven plasmas are simulating the chaotic magnetic reconnection, events that power solar flares, offering insights that could revolutionize space weather prediction. One team at Princeton even generated miniature magnetospheric bubbles using plasma guns, mimicking how planets deflect solar winds, a breakthrough that could inform designs for artificial radiation shields on Mars missions. The wildest possibilities lie beyond observation. Theoretical work on magnetic sails envisions spacecraft surfing interstellar magnetic fields like cosmic surfboards, using superconducting coils to ride galactic currents without traditional fuel. While still speculative, prototypes like NAS, a mag sail concept, show how manipulating these forces might one day enable slow but steady travel between stars. More immediately, studying how pulsars channel magnetic energy into particle jets could inspire next-generation plasma thrusters, turning astrophysical phenomena into practical propulsion. Yet the most profound impact may come from decoding magnetism's role in life's origins. Ancient rocks suggest Earth's field protected delicate probiotic molecules from destructive radiation, meaning exoplanets with similar magnetic shields could be prime targets in the search for alien life. Future telescopes like the Habitable Worlds Observatory will scan for polarized light signatures that betray these protective bubbles around distant worlds. What makes this era extraordinary isn't just the tools, but the convergence of disciplines: astrophysicists collaborating with quantum physicists to explore how magnetism operates at both galactic and subatomic scales, while engineers borrow principles from neutron stars to design compact fusion reactors. The next decade won't just solve old puzzles, it will reveal questions we haven't even thought to ask. As we pull back the curtain on cosmic magnetism, we're not just observers anymore, we're becoming active participants in a story written in lines of force, one where every discovery sparks new possibilities for exploring and understanding our magnetized universe. From the sun's rhythmic pole flipping to the ghostly magnetic whispers of long-dead stars, we've unraveled 30 cosmic enigmas that prove magnetism isn't just a footnote in astrophysics. It's the invisible ink writing the universe's grandest stories. Think about it, every flickering aurora, every spinning pulsar, even the delicate dance of planets forming around newborn stars, they're all governed by the same fundamental forces that once seemed confined to refrigerator magnets and compass needles. What makes these discoveries so exhilarating isn't just their scale, but their interconnectedness. The same magnetic reconnection that triggers solar storms might one day power fusion reactors here on Earth. The twisted fields around black holes could hold clues to quantum gravity. Even Europa's hidden ocean, revealed by its faint magnetic echo, teaches us how to hunt for alien seas light years away. These aren't isolated curiosities, they're pieces of a cosmic puzzle, each one reshaping how we understand everything from particle physics to the fate of galaxies. And the adventure is just beginning. With telescopes like the Square Kilometre Array coming online, we're poised to map galactic magnetism in 3D, while quantum sensors might soon detect fields so weak they've been invisible until now. Imagine uncovering magnetic fossils from the Big Bang itself, or watching an exoplanet's magnetosphere flicker to life in real time. The tools we're building today could reveal universes within universes, all woven from lines of force. So as we close this chapter, here's the real takeaway. Magnetism isn't just a force, it's a language. The sun speaks it in solar flares, pulsars stutter it in glitches, and distant galaxies paint with it across the void. And with every mystery we solve, we learn to listen a little better. Whether you're drawn to the violent beauty of Magnetars or the delicate balance shielding our planet, one thing's certain: the cosmos has more magnetic tales to tell. Now it's your turn. Which of these cosmic magnetic mysteries pulls at your curiosity the most? Is it the enigma of Mercury's stubborn field, the haunting glow of lunar swirls, or something else entirely? Drop your thoughts below. We're all part of this conversation. And if you've enjoyed this journey through the forces shaping existence, hit subscribe so you don't miss our next exploration. After all, the universe's greatest secrets aren't just written in starlight. They're etched in the curves of unseen fields, waiting for us to trace them. Until then, keep your compass handy. You never know when the next magnetic revelation